Okay, so we're going to do problem 8 from chapter 13. In this diagram, it shows that there are three 5-kilogram spheres are located at a distance. So this is located at 0.3 meters above particle B, and this is particle C that is located 0.4 meters away from particle B. Now, what are the magnitude and direction of the net gravitational force on particle B due to spheres NAC? Okay, so this is a very typical problem that we know that all these three spheres, they carry a mass. So when you have two masses placed together next to each other, they are going to experience gravitational force. So the question is, how do we calculate that gravitational force? This is particle B, so what you want to do is that you want to find the gravitational force acting on particle B due to the presence of particle A, and add the force that's acting on particle B due to the presence of particle C. So to start out with, you would say that the net force on particle B has two terms because the interaction is a pair particle. So you have FBA and then plus FBC. Okay, so in this case, let's think back. What is the equations for for two particles? So let's say particle 1 and particle 2. Then you would have Gm1, M2, and then the separation between them squared. So this is the equation when you have two particles separated by R sub 1, 2, and then this is the magnitude. What about direction? The direction of gravitational force is always attractive, which means that it is always pointing toward the other particle. So in that case, let's look at this slide. What we're going to do is that because this is a force, so you want to first of all calculate the magnitude. To calculate the magnitude, you use this equation to calculate the magnitude. Once you have the magnitude, then you want to use the diagrams here to indicate what is the directions of that force. Remember, the force is always attractive. So when particle B sees particle A, because it is attractive, so it has a tendency to move toward particle A. So the force acting on particle B due to the presence of particle A is in this direction. So this is your FBA. Okay? So you can see that it is positive because it's pointing upward. Now when particle B sees particle C, it is attractive, so it is going to be pointing toward particle C. So you have FBA and FBC with the direction. So what you want to do is that now plug in the numbers to that equation to calculate the magnitude. So let's do that. So your FBA is GMA, MB, and then the separation between them squared. The separation between them is 0.3, so you have your 0.3 squared. And then your G, all right, so let me just write out the equation and I'll write down the numbers later. So FBA squared. So what you have here is that your G value is 6.67 times 10 to the negative 11 times 5 over R1, RBA. So that's 0.3. So that's your 0.3 squared. So after you calculate your FBA, you should have the magnitude that is equal to 1.85 times 10 to the negative 8th, and that's in Newton. What about its direction? We know that FBA is pointing upward, so what you want to do is that now adding the vector sign in here, and then you have the J hat here. Okay? So this is FBA that's pointing upward. Now let's look at FBC. So FBC, you have G, MB, MC, and then RBC squared. So what you have here is that 6.67 times 10 to the negative 11, and then you have the phi and over RBC. So RBC here is 0.4. So you have your 0.4 squared. So what you have here at BC is that you have 1.0 times 10 to the negative 8, and that's in Newton. Okay? What about its direction? Because it's pointing rightward, so you have the positive I hat. So you have the individual force that one is pointing upward and one is pointing rightward. So now that express this, the net force is the sum of these two. So when you add them together, what you have here is that you have 1 times 10 to the negative 8th, that's I hat, and then plus 1.85 times 10 to the negative 8th J hat. Okay. So what we have here is that you have the force that is the net force that expressed in unit vector notation. Now, if you also find the magnitude, what you should do is that use Pythagorean theorem, and that will be this square plus this square. So when you do that, you will find the magnitude of that force is 2.1 times 10 to the -8 Newton. And because this is a magnitude, so you can just keep it like that. So this is the force. What about its direction? In order to find the directions of the net force acting on particle B, we need to again use the Cartesian coordinates. So you have a positive x here, you have the positive y components here. So the net force is actually pointing in that direction. So in that case, you can define this angle to be theta, and then calculate what is that theta. So when you do tangent theta, and that's equal to, so tangent theta here would just be this magnitude, which is at BA, over this magnitude, which is at BC. And then what you have here is that your theta, after you do the calculation, your theta will be 61.6 degrees. Okay? So this is a very simple problem. I say it's simple because you have the force component. They are in the either x or y axis in that direction. You might have an interaction that's actually off the axis. Then you have to resolve that vector into the x and y component and do the vector sum. Okay. Now, so we're going to do that later. So before we move on, I also want you to calculate that. Say you have these three particles arranged in this. What is the gravitational potential energy involved in this arrangement? Okay, so we calculate the force, and force is the magnitude. What about energy? Energy is a scalar, so and it involves you have the three particles arranged like this. What will be the gravitational potential energy involved in this arrangement? So let's see how do we do that. Now remember, when you have a collection of particles, the interaction is always between pairs. So you have to pair up particles, and then those particles should not repeat themselves. They should not pair with themselves. And then the order of pairing the two is the same. So you don't double count those let's say Fa that U12 is equal to U21. So you don't have to pair include that. So in other words, the net gravitational potential energy within that system, we have three particles. You should pair them. So we can pair AB and then AC. And after A have no more particles, then you run to the next one, which is B. B already paired up with A. So the only particle that hasn't paired up is C. So your U net is UAB plus UAC. So we start out with the first particle, A. And then after we run out the particles to pair it with, then we move on to the next one, which is BC. Okay? So we have AB, AC, and then BC. And then what we want to do is that we use the equations. So what is the equation for gravitational potential energy? That will be negative G, mass A, mass B, and then the separation between them. A and B, the separation is 0.3. So you have this. Remember, do not square it because this is energy. And then minus G, MA, MC, and then A and C, the distance between them, the distance connecting point A and point C, we can use the trigonometry. This is 0.3, this is 0.4, so you punch your calculator, you can calculate what this hypotenuse is, and this is 0.5. Okay, so we have 0.5 here. And then minus BC, so you have G, MB, MC, and then the distance between them is 0.4. So after you plug into those numbers, what you have here is that the mass is 5, G is the numerical value. So after you punch a number, you should get a value that is negative 1.3 times 10 to the negative 8th, and that's in joules. All right, as you can see, when we pair them R, we treat them as we just use the numerical value. We do not give it a direction. That is because energy is a scalar, so you don't treat that as a vector. So you just use this equation and then plug in a number and calculate the energy content within that system. So in that case, you can see that it doesn't really matter. It doesn't really matter, the forces, acting among among these particles, so long as the arrangement of these three particles are like this. The distance stays the same, then you will have the same energy content regardless what force is acting on which particles. Okay? So what I'm going to do is that I'm going to spice up the problems a little bit. So let's say in this problem you asked to find the force acting on particle B. What about if I ask you to find out the force acting on particle C? So in other words, you still have the same diagram, but now you're asked to find the force on particle C. So we start out with the same setup. Okay, we want to write our equation saying that the net force acting on particle C will have two terms. One is the interaction between A and C. The other one is the interaction between C and B. So in other words, Fc net is equal to the interaction between C and A, the interaction between C and B. Okay, so that's it. As I mentioned, whenever you do this kind of problem, calculate the magnitude first, and then use this diagram to see what is the directions of force. Okay, so FCA with the magnitude, that will be G, MC, MA, and then the distance between them. So C and A, the distance between them is 0.5. So 0.5 squared. And as you can see, because I'm using this equation to calculate the magnitude, so I don't even include the negative sign. Okay. So the negative sign is actually being implicitly taken care of when you consider the directions of the force. So let's see, when particle C sees particle A, it will have a tendency to pointing in this direction. So this is your FCA. So we can see that it is making an angle with the horizontal axis. So that's it. If we define this to be theta, then you can resolve this vector into the S component, which is negative, and the Y component, which is positive. So let's do that. So, but once you plug in the numbers, you should get this value, which is 6.67 times 10 to the negative 9 Newton. Okay, now I'm ready to resolve FCA into the X and Y component. Okay, so let's do that. FCA, in vector form, you have this magnitude, so you copy that down. And then your X component, that will be this times cosine theta. Your S component will be the magnitude, and then times cosine theta. And then because it's pointing in the negative direction, you have to put a negative sign in front of it. So it's negative, and then cosine theta, and that's your I hat. And then in the vertical, that's just sine theta, and that's positive. So it's plus 6.67 times 10 to the negative 9, and then sine theta, and then j hat. Okay? So what we have here is that negative 6.67 times 10 to the negative 9, and then cosine theta. So cosine theta here, you can calculate the theta. Oh, you can just use cosine theta based on this, this triangle, because it is cosine theta that you want, not the theta. So if you just look at this, using this right triangle, your cosine theta would just be 0.4 over 0.5. So that's 4/5. And then your sine theta would just be the 3/5. Okay? So in that case, your cosine theta will plug into this, so that's 4 divided by 5 I hat, and then plus 6.67 times negative 9, and then sine theta, that's 3/2, so it's j hat. So after you do the calculation, your FCA is equal to negative 5.336 times 10 to the negative 9 I hat, and then plus 4.002 times negative 9 j hat. So this is your FCA. This is just one force. That force, you calculate the magnitude first, resolve into the X and Y component. So we have this. And then the next is that what is the magnitude of FCB? The FCB is equal to, and we know that it is FCB. So FCB, when the particle C sees particle B, the direction is in this direction. So this will be your FCB. Okay? And that's leftward. So you have negative. So I'm going to put the negative because it is along the x-axis. You can just use this equation. So it's G and then MB, MC the distance between them, which is 0.4 squared, and then I hat, okay? And then so after you plug in the number, you should have the value that is negative 1.042 times 10 to the negative 8th, and that's I hat, and those are in newtons. So you have the FCA, that is this, and then you have your FCB, that is this. So you can do a vector sum. You add, because the net force acting on particle C is FCA plus FCB. So when you add them together, what you have here is that you will get, after you do the adding all the x components together, then you will get negative 1.57, okay, times 10 to the negative 8th I hat, and then plus 4.002 times 10 to the negative 9th j hat. Okay, so again, when you have the force that has the x and y component, you can, so these are expressed in unit vector notation. You can also do, you can also find the magnitude, which is just Pythagoras theorem, the x component squared plus the y component squared. So your FC net, you should get 1.63 times 10 to the negative 8th Newton. So that's the magnitude. What about direction? So again, when you want to find direction, you want to plot it on the x and y axis. So you have, for particle C, the force here is negative. It has a negative x component, but a positive y component. So the force acting on particle C will be pointing in that direction. So if that's pointing in that direction, you can define your, let's say, if we define this angle to be theta prime, let's calculate this theta prime first, and then use 180 degrees minus theta prime. That will give you the angle with respect to the horizontal x-axis. So tangent theta prime, remember we're using small angle, so you have to use, drop the negative sign. So that will be FCA, let's see, the y component. So the y component is roughly 4 times negative 9, and then your s component is 1.57 negative times 10 to the 8th. Negative 8th. Okay, so your theta prime, after you punch into the calculator, your theta prime should give you 14.25 degrees. And then if you want to express the vector in this, so you have 100. So your theta, so this is your theta. Your theta is 180 minus theta prime. So you will get 165.75 degrees. Okay. So you can see that when you have forces that is not along either the x or y direction, the process is actually a little bit more involved, because you have to resolve the vector into the x and y component before you can do a vector sum, with the other forces. Okay, so that is problem 8. And then the next one we want to do is problem 17. And let me just erase this. Okay, so problem 17. What would an object weigh on the moon's surface if it weighs 100 newtons on Earth's surface? Okay, so let's see. So let's draw a diagram. So the object what is the object on the moon? So I'm just going to call that WM. So what would that be when the same object that weighs, let's say, on Earth, that's 100 newton. If an object on Earth that weighs 100 newtons on the Earth's surface, what would the object weigh on the moon's surface? And how many radii must this same object be from the center of Earth if it's to weigh the same as it does on the moon? Okay, so let's say you have that's it. We start with the numbers we're given. You have an object that weighs 100 newton on the surface on the surface of the Earth. So we can calculate the mass, right? So the mass based on this, that will be, and the mass is actually constant regardless where it is placed. So your mass is WE over the gravitational acceleration on Earth. So I'm just going to put a E here because now we have like two different objects. So now we have 100 over 9.8. So the mass of the object is equal to this 100 divided by 9.8. Now the gravitational acceleration on Earth is 9.8 meter per second squared. And the gravitational acceleration on the moon, which I call that GM, and that's equal to 1.67 meter per second squared. So once we calculate the mass, then we can calculate how much does it weigh on the surface of the Earth, because on the surface of the moon, because the weight is simply equal to mass times the acceleration. So you have the mass. And you have the acceleration. Now it is the acceleration of the moon. So you can just plug in the numbers. So that will be 100 over 9.8 and times 1.67. So what you have here is that this will be the weight on the surface of the moon. If an object weighs 100 newton on the surface of the Earth, then this is the amount. This is how much the same object will weigh on the surface of the moon. And then in the problem, and part B says that what would be where would the objects be that weighs the same? If you have on the surface let's see, what is part B? So you're asked about how many Earth radii must the same object be from the center of the Earth if it's to weigh the same as it does on the moon. So in other words, this is the Earth. You're asked to find where would the objects be. So that measuring from the center of the Earth, and this is the RE, the radius of the Earth. How many radii would that be if the same object weighs the same as is on the moon, and which is 17.08, 0.04. So in other words, you know the weight right here, but you don't. And we know that when it goes farther away, then it weighs lower. So how do we solve the equation? So to solve the equation, realizing that the weight is equal to mass of the object, and then times the acceleration, okay? And we call acceleration is mg, and this g is now because it's away, it's not on the surface of the Earth, so you will actually use the GMN. So that's use g, mass of the object, mass of the Earth over the separation. Okay, so because the weight basically is a gravitational force squared. So in other words, the weight now is 17.04, and then where should you place the object so that the weight is 17.04? Your g is gravitational acceleration, and your m is the mass of the object, which is 100 over 9.8, and then this is the mass of the Earth. So that's plug in the number. So 17.04 is equal to 6.67 times 10 to the negative 11, and then times 100 over 9.8, the mass of the object, and then times the mass of the Earth. The mass of the Earth, if you go flip to the back of the book, it will give you all these numbers. So it's 5.98 times 10 to the 24th, and then R squared. What is your R? Your R is the one that we are asked to find. So after you plug in the numbers, you'll find that your R is equal to 1.5 times 10 to the 7 meters. So in other words, measuring from this point to this point is 1.5 times 10 to the 7 meters. And you're asked to find how many radius from how many radius. So how many radius? That will be basically use this number. So you have 1.5 times 10 to the 7th divided by the radius of the Earth. And the radius of the Earth, again, you can find that information in the back of the book. That's 6.37 times 10 to the 6th. And what you have here is that it's about 2.35 radius of the Earth. So in other words, at this point, So you have the same object, and then it weighs 100 newtons on the surface of the Earth. When you move, the object away, the farther away the gravitational force acting on the object is less. So eventually, at some point, it will weigh about 17, and your task is to find how far away should the object be placed with respect to the center of the Earth. That will give rise to the gravitational, the weight that's about like 1704 newtons. Okay, so that's that.